Hello everyone, welcome back to another optics video. Today we will shift from our normal basics of optics series and talk about the physics behind lasers. So let's take a look at a high level overview of what a laser is. Look at the green light bulb on the left. It emits photons or special subatomic particles in all directions, and when these photons hit our eyes, our brain processes it as light. And because it scatters in light in all directions, it's really good at illuminating rooms or large areas. But suppose we can control all these photons and have a device emit them in a narrow straight line with high intensity. This is effectively what we call a laser, like the image on the right. It emits a straight, narrow, and concentrated beam of light. Believe it or not, laser is actually not a word, but is an acronym that stands for Light Amplified by Stimulated Emission of Radiation. It may seem like a lot of arbitrary terms, but we'll make sense of it later on. The four key principles of a laser are listed below. Lasers are monochromatic, which means the light they emit has a very small range of wavelengths. Recall that the electromagnetic spectrum we learned about in the previous video. Lasers emit light that is not a combination of all the wavelengths, but rather a specific wavelength or small range of wavelengths, producing a distinct color. Lasers also emit light that is coherent, which basically means that the waves travel in sync with one another, like walking next to your friends on the sidewalk. In this scenario, you and your friends walk in line with each other instead of being staggered, just like the light that comes out of a laser. The light emitted is directional, meaning that all light travels in a single direction, which produces the straight beam we see. Lastly, the light that comes out of a laser is intense, which just means that it's very powerful and concentrated, which is necessary in certain applications, as we'll explore later on. Let's dive into detail on how this works on an atomic level. Suppose this diagram represents an atom at its ground state, or an atom with little to no energy called E1. If we shoot a photon at it like this, the atom is charged with the energy of the photon and jumps to a higher energy level, E2. Now this process is called stimulated absorption because we stimulated the atom and it absorbed the energy of the photon. Eventually, the atom will want to return to its ground or lower energy state, and consequently, the atom releases energy in the form of a photon, the same energy it was originally stimulated with. This is called spontaneous emission because the atom emitted a photon but did so on its own, spontaneously, without being stimulated by anything. But this isn't exactly what we want because we can't control the way a photon moves, a crucial element of a laser. Suppose this atom has already been stimulated with a photon to be at energy level E2. In this scenario, what happens if we shoot another photon at it? Let's look at what happens. In this scenario, two photons are released from the interaction and the atom returns to its ground state. This is called stimulated emission because we stimulated the atom, causing it to emit two photons and return to its ground state. A key note is that the two released photons are coherent and directional, two key requirements for a laser. A small technical detail that allows this reaction to occur is that the incident photon, or the one that originally stimulated the atom to energy level E2, has a frequency that corresponds to the energy difference between the two levels. Recall that on the electromagnetic spectrum, frequencies and wavelengths of light both correspond to the amount of energy it has. Now let's look at a simple diagram of a laser. The laser medium represents all the little particles or atoms that are ready to be stimulated. This pumping process you see on the diagram refers to charging these atoms and causing stimulated emission to occur. R1 and R2 are both mirrors that cause the atoms to bounce back and forth while also being pumped and charged to increase the intensity. R2 will usually be less reflective than a mirror, such that some light can escape, producing the laser output that we see. Here's a basic simulation to better visually understand what's going on inside a laser. Notice that when we shoot these electrons that don't have the same energy difference or wavelength because they're related, we can see in the top right that the energy does not match this red bar here, which means that the atom is not going to be stimulated. Now let's just change the wavelength with this slider until it matches just right with the energy level. And we can see that the atom is being stimulated. However, it is just jumping back down to its lower energy state by itself and emitting an photon. And remember that this is called spontaneous emission, which is cool, but it's not what we need for a laser. So I'm just going to increase the amount of photons that we're shooting out from this simulation here. And we can see that the atom is being stimulated again when it is already stimulated to its higher energy state, which causes stimulated emission. And you can see these coherent photons which are in phase with each other, these pairs that are coming out on the other end, which is what we want for a laser. So what I'm going to do is add two mirrors here to trap the photons bouncing between each other. And remember that they will get more intense as they bounce back and forth. And if I just decrease the reflectivity on the right side, you can see I'm letting some some photons through, and these are coherent and have the same direction, which causes a laser beam. And so now that you know about how a laser works, what are some of the applications of this technology? In the medical field, lasers have already been in use for surgery like LASIK. And also recently, lasers have been used in some forms of targeted cancer treatment. In the manufacturing industry, we see lasers used for welding and types of 3D printing. Another big industry for lasers is the telecommunications sector, which uses lasers in fiber optic communication, which some people have implemented into their home Wi Fi network, and also in satellite communication, where lasers are used to transmit data between satellites and ground receivers on Earth. Lasers are also in use in military, like guided missile technology and concentrated energy weapon systems. After you watch this video, see if you can explain the answers to the questions on screen to a family or friend. I hope you enjoyed this video, and I'll see you again soon.